You know, there's this hidden language all around us. It's the language of mathematics, a powerful code that describes everything from the swirl of a galaxy to the arch of a bridge. Today, we're going to unlock three key parts of that language: surds, indices, and logarithms. And you'll see how they connect our world in some pretty unexpected ways. I know, it sounds like a weird question, right? But the secret lies in the numbers. Specifically, the kinds of numbers engineers have to use to get the exact, perfect dimensions from massive structures like this, so they can stand for centuries. And the foundation for all that precision is a type of number that was once a complete mathematical mystery. You heard that right. Way back in 1150 BC, a mathematician named Gerardo of Cremona was playing around with Pythagoras' theorem and stumbled on something new, a new kind of number. He called it voiceless, in Latin, Surds, because these numbers couldn't be spoken or written down cleanly. It was like they were a mathematical ghost. So, here's our game plan. We'll start with those mysterious, voiceless numbers, the surds. Then, we'll figure out how to work with them. After that, we'll unlock the incredible power of indices, see how they're connected to their inverse, logarithms. And finally, we'll put it all together and see this language in action. All right, let's dive right in with those so-called voiceless numbers. What is a surd, really? And why did it give early mathematicians such a headache? Okay, so a surd is basically just a root that you can't simplify down to a nice, neat whole number. Think of the square root of 2. Your calculator will tell you it's about 1.4142135, but that decimal just keeps on going forever, and it never repeats. That endless chaotic quality is what makes it irrational, and that's the very definition of a surd. This slide makes the difference super clear. On one side, you have numbers like the square root of 2 or 3. Their decimals are just wild and go on forever. Those are surds. But on the other side, the square root of 4 is 2, the square root of 9 is 3. They're clean, predictable, rational, and so they're not surds. So you might be asking, why even bother with these messy numbers? Well, it comes down to one word: precision. A calculator has to round that number off eventually. It gives you an approximation. But the symbol, root 2, that represents the exact value. And for an engineer building a bridge, an approximation isn't good enough. You need perfection. That's why surds are so crucial. Okay, so surds are precise, but they definitely seem a little wild. The next step is to figure out how to tame them, how to simplify them so we can actually use them in our calculations. Let's try one. Take the square root of 12. The trick is to look for a factor that's a perfect square. In this case, it's 4, right? Because 4 times 3 is 12. So we can split it into the square root of 4 times the square root of 3. We all know the square root of 4 is just 2. So our final, simplified answer is 2 root 3. See? We've tamed it. Now, there's this little rule in math, sort of an unwritten code of conduct. You're not supposed to leave a surd in the denominator, the bottom part of a fraction. It's just considered messy or unsimplified. So how do we clean it up? There's this really cool trick called rationalization. It uses something called a conjugate. It's a fancy word, but think of it as the surd's mathematical twin. When you multiply the top and bottom of the fraction by this conjugate, something almost magical happens. The surd in the denominator just cancels itself out, leaving you with a nice, clean, rational number. Okay, get ready, because we're about to shift our perspective in a big way. We've been looking at numbers through the lens of roots, but there's another, much more powerful way to think about them. And that's where indices come into play. So, by now we know how to do this. We see the square root of 75. We immediately hunt for a perfect square factor, which is 25, and we simplify it down to 5 root 3. Straightforward stuff. But what if I told you that little root symbol isn't the whole story? What if there's a completely different notation that connects this whole idea to a different part of math? And here it is. This is the big aha moment. A square root is nothing more than a fractional power. The square root of a is just a to the power of 1/2. This is huge. It means all the rules that we have for powers, or indices, can now be used for roots. We've just translated one part of the language into another, and this new one is way more versatile. And by seeing roots as powers, we suddenly unlock this amazing toolkit. These are the laws of indices. When you multiply, you just add the powers. When you divide, you subtract them. Anything to the power of 0 is always 1, and a negative power just means you flip the number into a fraction. These few simple rules govern all kinds of exponential relationships.
In math, everything seems to have an opposite, right? Addition has subtraction, multiplication has division. So, what's the opposite of raising something to a power? What's the undo button for an exponent? Well, that's where logarithms come in.
Take a look at this. They're just two sides of the exact same coin. The index form is a statement, a raised to the power x equals the number n. The logarithm form just rephrases that as a question. To get the number n, what power do I need to raise a to? They are perfect inverses of each other.
Seriously, don't let the log notation scare you. Every single time you see it, just translate it into that simple question in your head. A logarithm is just a power finder. That's its entire job.
Let's make it real. What is log base 3 of 81? All it's asking is 3 to the power of what gives you 81? Well, let's see. 3 times 3 is 9, times 3 is 27, and times 3 again is 81. We multiplied it 4 times, so the answer is just 4. See? It's just a question. So, we've learned the grammar of surds, the vocabulary of indices, and the inverse logic of logarithms. Now for the really fun part. Let's put this new language to the test with a real-world problem. So many things in nature grow exponentially. They don't just add, they multiply. A classic example is a bacteria culture, where the population can double in an incredibly short amount of time. How can we possibly model that kind of explosive growth? This is where our knowledge of indices becomes a superpower. Let's say we start with 100 bacteria. They double every hour, so our growth factor is 2. After 5 hours, the calculation is just our initial amount, 100, multiplied by 2 to the power of 5. 2 to the 5th is 32. So 100 times 32 gives us 3,200 bacteria. That language of indices describes this growth perfectly. So just think about that journey. We went from a voiceless number that ancient mathematicians couldn't even explain to a powerful set of tools that can describe the world all around us. It really makes you wonder, doesn't it? What other secret codes and powerful languages are still waiting to be discovered, hidden inside the world of mathematics?